How does NumPy array indexing work so fast? Have you ever wondered why NumPy array indexing is so quick? Let's break it down in a way that makes sense. First off, NumPy arrays store data in a contiguous block of memory. This means that all the elements are laid out next to each other. When the computer accesses these elements, it can do so much faster because it can load multiple elements at once. This is thanks to something called cache lines, which help reduce the time it takes to get data from memory. Now, let's talk about how NumPy calculates where each element is stored. Each array has a feature called strides. Strides tell the program how many bytes to skip to get from one element to the next. When you want to access an element, NumPy simply multiplies the index by the stride and adds an offset. This calculation is super fast because it is done in compiled C code, which is much quicker than regular Python code. Another reason for the speed is that NumPy avoids the overhead that comes with standard Python. Indexing in NumPy is optimized and does not involve Python loops or dynamic type checks. This makes a big difference in performance. There are two types of indexing in NumPy, basic and advanced. Basic indexing uses slices or integers and returns views of the original array. This means it does not create copies of the data, keeping things fast. Advanced indexing, on the other hand, uses arrays or Boolean masks, which can create copies. While this is slower than basic indexing, it is still faster than using pure Python operations. Memory locality is also important. Since NumPy arrays are stored in a predictable order, accessing elements in sequence is efficient. This takes advantage of spatial locality, which means the computer can load data more effectively. When you access elements that are next to each other, you get fewer cache misses, leading to quicker access times. When you index a NumPy array, especially with slices, it often returns a view instead of copying data. This means that no new memory allocation happens, saving time and resources. Lastly, all elements in a NumPy array have the same fixed data type and size. This uniformity allows for straightforward calculations when determining the position of any element, making the process even faster. In practical terms, this means when you use NumPy for data analysis, you can slice and index large datasets efficiently. This allows for quick data selection and manipulation without the slowdowns that come from using standard Python lists. This is why NumPy is a go-to tool for numerical and scientific computing in Python.